In this video, we'll learn to evaluate integrals involving quadratic functions. Suppose we have an integral f of x is integrand. Now, if the integrand contains ax squared plus bx plus c anywhere, then we said this is a kind of function that involves quadratic form, and this is a quadratic form. And the quadratic form could appear in the denominator in fraction, if f is a fraction, or could be under square root sign, could be anywhere. How we deal with this kind of quadratic form is we try to first of all complete a square. That's algebra. So we can always turn this quadratic form to something like x plus a number minus a number square plus some other number. So we turn this into two terms: the sum of a square involving x and the number. Now this number could be negative. And then, depending on the signs of a or this, we can try to introduce some tricks of solution and turn this into a trig integral, then evaluate. So the key is to complete the square. Now let's see how we complete the square. Just quick review. Let's first start with 5 plus 12x minus 9x squared, quadratic form in algebra. The way we complete a square is we try to add a number to the expression so that the x squared term and the x term can be turned into a perfect square. Now I usually arrange powers of x in descending order, then turn the coefficient of x squared to 1 by factoring out the coefficient. So let's factor out the negative 9. Only from those two terms. We don't need to worry about the 5. Just copy it down. And then simplify inside here. It's going to be negative and cross out 3. I'm talking about this is a 4 over 3x. Now inside parentheses, I'm going to try to come up with a number with which this x terms can be turned to a perfect square. The number we need is square of half of the coefficient of x. Okay, so half of 4 over 3 is going to be 2 over 3. So it's a negative 2 over 3 squared that I need. So I add square of negative 2 over 3 to the expression. These 3 terms were turned to a perfect square. Here you see. At the same time, I'm subtracting this number 2 because I don't want to change the value of the expression. With plus and the minus at the same time, the expression is same as before. Now those terms under 9 becomes a perfect square. You can verify, you can multiply this out, you get all those 3 terms back. And this number, simplified, becomes 4/9. Now we can multiply -9 through. -9 times -9 cross out is 4, so it's 9. Or I can rewrite it as 9 minus 9x minus 2/3 squared. This way we completed the square, the given quadratic polynomial or quadratic form. Let's see another example. So we're given 4x squared plus 4x minus 3. Again, I'm going to factor out the 4 from the first 2 terms. So we turn the coefficient of x squared to 1. The constant term stays. As you saw in the first example, the constant eventually get combined with some number we would throw in there. Okay, this time coefficient of x squared becomes 1 now. What we need, just like before, is half of the coefficient of x. Coefficient of x is 1, so half of it is 1/2 squared. So I added half squared and then subtract at the same time to keep it balanced, unchanged. So this expression is the same as before. We added this one just so it's possible to turn this 3 into a perfect square. Now those 3 terms becomes x plus a half square, which is actually pretty easy to do mechanically. Just put the x down here, put the half down here, or the previous example, put the x down here, put a -2/3 down here. So you can see when the coefficient of x turns negative, you get the negative. When the coefficient of x is a positive, you get positive or plus. Now I already got the perfect square. This number doesn't have to be in the form of squares. Square it out, then multiply 4 through. 4 times half, not half, 4 times 1/4 is 1. -1, so it's -4. So again, we completed this square in this quadratic form. Now let's see how we evaluate function involving quadratic form like this, in general like this. Well, to save time, I put this integral here that involves the quadratic form we already worked on. So with the completed algebra work, we already turned the quadratic form 5 plus 12x minus 9x squared into this. So I'm going to just cut it down. 9 minus 9x minus 2/3 squared dx. The rest is to try to come up with some appropriate trig substitution. Let's look at this. 9 minus expression, so we hope this expression to be like a sine square. To take advantage of the trig identity, 1 minus sine square equal to cosine square. This is how we try to come up with appropriate trig substitution. So let me write it down. So here this term, we want this to be sine square. In this expression, those two numbers actually match, so we just really need the square term to be sine square. See, now cross out the 9, so x over x minus 2/3 square equal to sine theta, and take square root and solve for x to get our substitution. This is basically a trig substitution. Now 9 minus 9 times the square term becomes 9 minus 9 sine square. And we pull out the 9, it will become 1 minus sine square left, which is cosine square. So with this trig substitution, you can see this term, which came from the original quadratic form, becomes a 9 cosine square. Now the x is replaced by sine theta plus 2 over 3, and the dx becomes cosine theta d theta. Alright, well, we just simplify this integral to see how to evaluate these tricks involved. Square root of 9 is 3, so pull out 1 over 3. Cosine square, square root is cosine, actually cancel out with the cosine there. So we're left with actually just sine theta plus 2 over 3. Fortunately, these are all very easy to integrate. Integral of sine is negative cosine. Integral of 2 over 3 is just theta plus c. Now, just like how we turn expression in theta back to expression in x, we need to create a right triangle. Let's see, our substitution is x equal to sine plus 2/3, so we need to actually solve for cosine. This is the sine. Let's write it as a fraction so we can associate expression with the length of the sides of a triangle. So basically just combine into 1. X minus 2/3 becomes 3x minus 2 over 3. Just multiply top and bottom by 3 and put them together. So this suggests that if we think of this angle as a theta, then 3x minus 2 is opposite side, 3 is the hypotenuse. The third side, if you use Pythagorean theory, it becomes 9, which is square of that 9. Already squared 3, so this is a 9 minus 3x minus 2 squared. Now, back into our answer. In theta, we see the cosine, according to our triangle, is going to be this radical divided by 3 adjacent. 9 minus 3x minus 2 squared over 3. And the theta, where theta is outside any trig expression, so cannot use the triangle to do it. Instead, we need to rely on the substitution. Use the brute force to solve for theta. Pretty simple, just take inverse sine on both sides. So theta equal to inverse sine of 3x minus 2 over 3. Plus this is the final answer. Okay, so this is an integral involving quadratic form. The key is to complete the square in this quadratic form. It's algebra. Once you come up with a perfect square, you just check out whether it's a difference of two things or sum of two things in the order to come up with some trig substitution. With the trig substitution, you turn this into a trig integral. Evaluate trig integral to get the x back, relying on some right triangle, and in this example, the substitution itself too. Alright, let's see another example. Again, I already work out the algebra needed to complete the square here. According to our earlier work, the 4x squared plus 4x minus 3 is the same as this square minus 4. Now, let's again work on the side to see what trig substitution we need. Well, this is a square minus number, so we want this to be secant square. It's a secant square minus 1 equal to tangent square. So let's try this. 4 equal to 4 secant square. Solve for x, so divide by 4, take a square root, both sides, move it half over, so we can easily come up with the trig substitution. Same time, the expression here becomes 4 secant square minus 4, which is the same as a 4 times secant square minus 1, or 4 times tangent square. Now the denominator becomes this one term, 4 tangent square. The top, just plug in 3 times secant minus half plus 2, where the dx becomes secant tangent d theta. Secant theta tangent theta d theta. Now this 4, well, it's constant, we can always pull it outside. Tangent and tangent square cross out, so there is only one tangent left on the bottom. Let me write it down. Also on the top, we can kind of simplify it a little bit too. So it's a 3 secant minus 3 over 2 plus 2. There's still tangent here, still secant here. Now we can divide each every term by tangent and also multiply secant through. So let's see. We're going to have actually 2 separate integrals. So the first one with the 3 and the secant square over tangent. Secant multiplied through secant square. There's tangent on the bottom. There's a 3 for up. Now the second one, let me combine the coefficients first. So it's 4 over 2 and the positive 1/2. With the secant on the top, tangent on the bottom, d theta. Now this is actually pretty simple integral, because the secant square is like a derivative tangent, so I can tell right away if I use u equal to tangent, this integral becomes fairly obviously 1 over u du. We'll get the log. Second one, see what we have here. I have a secant over tangent. It's not quite clear how we do it. Well, you can always turn everything to sine cosine. What's secant? Secant is 1 over cosine. Or tangent on the bottom is like cotangent here. And cotangent is cosine over sine. So while the first integral is pretty simple, it's just log u. Second one is not quite. Let's see. So the cosine cancel out. That just says you're gonna have just 1 over sine, which is cosecant here. Log, let's get that back. It's log tangent theta. Well, the cosecant theta, there's a formula we can use. According to table of integrals, integral of cosecant is negative log cosecant theta plus cotangent theta, all multiplied by 1/4 outside. Again, we need to create a right triangle based on the substitution in order to get rid of theta. Look at our substitution. Our substitution basically says secant is x plus 1/2, or 2x plus 1 over 2. This way we can tell if this angle is theta. Secant is 2x over 2, and secant is 1 over cosine. So cosine is 2 over 2x plus 1. In other words, in our triangle, 2 over 2x plus 1. And the third side, I may or may not need it. I probably need it. Well, let's see. The third side will be square root of 2x plus 1 squared minus 4. Again, we would use Pythagorean theory to determine that. So let's see. Let's multiply the 1/4 so we don't even have parentheses all over the place. The first one is 3 over 4 log tangent. I need tangent here. What's tangent? Tangent is opposite over adjacent. Over adjacent. The second term, 1/4 multiplied through, so it's 1/8. And there's a negative sign. Yeah, let's put the negative in the front. So log inside cosecant. Well, what's cosecant? Cosecant is 1 over sine. So let's figure out sine first. Sine is opposite over hypotenuse. So cosecant is the reciprocal, which is 2x plus 1 over plus cotangent. Well, cotangent is 2 over that. And this is our answer, which can be simplified probably more because of the properties of log, so on. For example, the first term, you can take a log of the top, log of the bottom, then the bottom becomes a constant which can be combined with the opposite constant, so we'll be left with only log of the top. Log of the top is half power, so you can actually even get the half power down as 8 here, plus the 1/2 log. Eventually you have 2x plus 1 squared minus 4. Also, the log, the terms inside the second log, you can clearly combine them into 1, and then use the property to split this up. If you split, you can get a similar log like that. So there's a lot of probably simplification that can be done. We don't care about how far we can simplify. this kind of problem, the main thing is what do we do with the quadratic polynomial? Complete square, then you try to come up with some kind of a trig substitution, turn this into a trig integral. Evaluate. We learned to evaluate the trig integrals before, so once we have the correct substitution, trig substitution, the rest pretty much like how we evaluate trig integrals, evaluate the integral with the trig substitution before. Alright, so we see how to evaluate the integrals involving quadratic form. With the discussion here, actually, if we recall before, let's just quickly talk about something we did before. Partial fraction, p over q, rational function. Remember, the denominator depends on what kind of factors denominator contains. Could contain first order factor, non-repeating or repeating, or second order, non-repeating or repeating. It's when it's a second order before, really, in theory, if we have ax squared quadratic form, bx plus c, we assume the p over q to be second order, so ax plus c over the second order. That's the theory. So this would be partial fraction to be included in the decomposition. But actually, in the problems we worked on, the second order factor were all very special second order. There's no first order term. It was always like x squared plus 1 or x squared plus 4, that kind of special second order factors. Now we know what to do with the general quadratic factor or second order factor, so we could have first order term in there when dealing with rational function that involve partial fraction method. Alright.